Video, I'm going to take on this subject of marginal analysis, and this allows us to do what-if scenarios and determining what are the best inputs for the best least cost production and so forth. So this is really important for planning out a project, right? So we're going to look at cost functions, we'll see how to optimize them, and then a couple of key ideas, and then we'll be done. So we should be able to do this within 10 to 15 minutes. So what are they? What are optimal cost functions? I'm looking for a function that combines the input cost function of physical resources, so the unit costs of x's and you add them all up, right? And then the production function. Combine those two things to come up with a cost function that includes both. And why would we want to do this? Well, provides a measure of this cost effectiveness. How will the cost change given a change in a product that we're providing? And then it's a good way to determine the size of a project, for example. And we can figure out whether we have economies of scale in a particular situation or not, which is important. I'll explain economies of scale later on. So let's say we have this production function, just made it up, and this cost function. Okay. It's kind of a linear combination of inputs. And for optimality, what we want to do is minimize the cost for the production function, or said another way, we want the cost that's subject to the production function that we have. So it's a constraint. The production function is a constraint on the combinations of inputs that we'll be able to use. That's really what we're saying. So the cost function is really just the cost function from before, the combination of x's. But that's subject to the production function, where the output is y, and that's the combination of another combination of x's. So typically we have just these two things. So one constraint, and it's an equality. So it's a little easier than the other stuff we were talking about before. So this is the Lagrangian that sets this up. And if I go through this process, the first derivative with respect to any of the x's is equal to the first derivative of x with respect to x. I'm sorry, the first derivative with respect to the cost function with respect to any x, minus the Lagrangian times this function, right? Y drops out with respect to x. And I know that, or I'll define this. I've defined the marginal product before, but this right here is the marginal cost. It's the unit increase or decrease in cost given some unit change in x sub I. That's what this is, marginal cost. How much more is it going to cost me, or less will it cost me, if I change xi by some amount, by a unit amount? And then the marginal product, where you're familiar with, right? This is just the production function with respect to a change in x sub I, right? Times the Lagrangian multiplier. So that equals this ratio. And notice this is for any x. So for every x, the marginal cost over the marginal product is a constant. Right? It's equal to, for x1, x2, however many x's you have. So we can use that, right? So let's say we have this function, as I said, and this is the cost function. And let's do the marginal product with respect to x1, with respect to x2. We know this, right? So we're going to do the marginal cost with respect to x1 is 1. Respect to 2 is this. So I can use this. Right? I can use this idea to plug this in, and the y's go away, and I can calculate what the relationship is between the x1 and x2 that will give me the optimal or minimal cost. And what I want to do here is get a function of c with respect to y. So I want y inside here. So I'm going to play around with this a little bit. I know that x1 equals x2 to the 1.5, so I'll plug that in here and come out with y as a function of x2. And I also know this, so I know c is a function of x2. If I take this down here and solve for x2, then I can combine these two functions here. And find the function, the cost function, as a function of the output, the production. And this is the equation. Well, actually, this is the equation. So what use is that? Well, now I can find what the optimal cost is for any given output. The minimum cost will be. Now, harken back a little bit. This is the isoquant for this function, production function, or the what do you call it? The contour line for this function. And I don't remember if I mentioned the expansion curve, but I think I did. Marginal product, change in marginal product. This is the expansion curve is the line of maximum change along the surface. So it's always perpendicular to all of the isoquants. So if you're running down a hill, which direction should you run to go fastest, right? So if the cost increases at a slower rate than y, then we do have economies of scale. Economies of scale means if I increase my production, how much does the cost increase? Does it increase at a slower rate? So for example, if I double my outputs, does the cost double? If it does not, if it is less than double, then I have economies of scale. If it's more than double, then I don't have economies of scale. So with this example that we just did, I have these two things. So what I'm going to do is I'm going to increase y, and this marginal cost with respect to y should decrease. The marginal cost, the amount that this thing increases, should decrease if I have economies of scale. So let's take a look at this. Well, you can see right away as y increases, the marginal cost decreases. Increases also. And I did it over here with all of the numbers. But this is the general rule. If alpha is less than 1, then we have economies of scale. So the marginal cost is this. So if we do the example, alpha is 1.04. This is the marginal cost. Let's bring this up again here. There's the cost function, there's the marginal cost function. For y equals 1, the cost is 0.97, the marginal cost is 0.97. But for y equals 6, cost is 6 plus, and the marginal cost increases. So we don't have economies of scale. The marginal cost is still increasing. Whereas if we do another example where alpha is less than 1, like this is our production function. This would be our marginal cost function. I'm sorry, this is a cost function, not the production function. And this is the marginal cost function. For y, the same numbers as before, but for 6, the cost increases, but the marginal cost decreases. So as I increase y, the increase in the cost is not as fast as the increase in y is. So we have economies of scale. There's some other little things to look at with economies of scale that are not really related to a production function. So for example, if I buy more, in bulk, we all know, this reduces unit prices sometimes. Big businesses often get better deals just because banks have more confidence in them. Small businesses are generalists typically, right? So if you have experts doing your business, generally you'll have fewer mistakes, better operation. Not always, but generally. Technical things, big businesses are better able to buy higher tech. So better equipment, more efficiencies, lower costs. Marketing is better in big businesses. They can spread the costs around. Scale does indeed matter. Now, you may think, well, okay, we should do a big business then. Well, there are some diseconomies of scale with big businesses. Workers get lost in the crowd. They may, this may cause problems in the workforce. Bureaucracy increases costs. Slower communication. Sometimes more mistakes are made, and so forth. So that's a really quick and dirty take on marginal analysis.